Welcome to the fourth weekly session of the 2026 Demystifying Medicine series, jointly sponsored by the Foundation for Advanced Education in the Sciences and the National Institutes of Health. The series began in 2003, organized by Dr. Irwin Arias, who's been the guiding light for this popular series for the past 24 years. I am Harry Malik, Chief of the Genetic Immunotherapy Section and Deputy Chief of the Laboratory of Clinical Immunology and Microbiology at the National Institute of Allergy and Infectious Diseases. I've been asked by Dr. Arias to serve as moderator for today's presentations regarding the use of the current generation of cutting-edge genetic analyses tools as applied to informative epidemiology to transform medicine. Dr. Pardis Sabeti, our first speaker, will tell us how these genetic tools, together with epidemiology, can inform our understanding of and preparation for potential infection pandemics. Dr. Stephen Chanik, our second speaker, will tell us how these genetic tools, together with epidemiology, can inform our understanding of and response to a radiation exposure with respect to cancer risk and follow-up. The Demystifying Medicine series is designed to bridge the gap between advances in biology and their application to major human diseases by connecting the silos of knowledge and technology that may sometimes separate fundamental basic research and the application of that research to medical advances that benefit patients, or in the case of today's lecture, to also benefit society as a whole with respect to events that impact the health of populations. But equally important is that the observations in the clinic impact advancement of basic science work needed to discover new principles of biology and new technologies that may be applied to benefit medicine. This series is not meant to simply be the presentation of the latest complex science and medicine advances to scientific and medical specialists in the field, but rather the mission is to demystify these topics to make these advances understandable to the non-specialist that may include students, fellows, and interested laypersons, but also engaged specialists in the field. Note that the continuing medical education credit for attending today's lecture is available using CME code 67267 through the Johns Hopkins University School of Medicine as the CME provider. I will also need to mention that unfortunately next week's Demystifying Medicine is being postponed because of some scheduling issues. Next slide, please. As already noted, this session will examine how the current generation of cutting-edge genetic tools as applied to informative epidemiology can transform medicine. Understanding how we can remain vigilant for and responsive to emerging diseases, including those with pandemic potential, is essential to managing and assessing those medical risks. Dr. Pardis Sabeti will be addressing this topic by reviewing the Sentinel Initiative, which is a locally led model for global pandemic prevention. This initiative coordinates with regional laboratories and public health systems to apply genetic and other detection and analysis tools integrated with epidemiologic data to achieve early identification of emerging infection threats. Understanding the effects of low to moderate doses of ionizing radiation is essential to managing and assessing the risks of medical use of radiation for diagnosis and treatment, the risks of work and home environmental exposures to low-dose radiation, and of course the risk of major accident events that lead to widespread low-dose radiation exposure, such as the Chernobyl accident. Dr. Stephen Chanik will be reviewing the long-term epidemiology and genetic effects of the Chernobyl accident to inform understanding of how and why cancer develops in some patients but not others. More specifically, he will be reviewing the development of papillary thyroid carcinoma that is associated with radioactive iodine exposure in children, and he'll also review what is known or not known about the intergenerational effects of this radiation exposure event on the children of workers exposed during cleanup of the Chernobyl event. The common theme of these two presentations is to outline how innovative epidemiology and the current genomics tools can be used together to bring to light the otherwise invisible threats to the health of both individuals and populations at risk, thereby allowing the timely identification of the medical threat and the initiation of a preventative and/or management response. Next slide, please. Our first speaker today, Dr. Pardis Sabeti, holds several positions at the Broad Institute and at Harvard University, including Harvard Medical School. She is a leading expert in genome biology and molecular diagnostics as applied to emerging infection risks and pandemic risk. Her lab has created some of the most widely used algorithms and powerful molecular tools to mine the human genome for beneficial and protective genetic elements, as well as transformative methods for diagnostics and gene delivery of new biomedicines. She's applied such approaches to track and detect viral pathogens in real time, including Ebola, Lassa, Zika, SARS-CoV-2, influenza, malaria, and Lyme disease. She is also co-founder of Sherlock Biosciences and Delve Bio and a member of the National Academy of Medicine. Our second speaker today, next slide, Dr. Stephen Chanik is Director of the Division of Cancer Epidemiology and Genetics at the National Cancer Institute and Senior Investigator in the Laboratory of Genetic Susceptibility. His research focuses on genetic susceptibility to cancer, including the discovery and characterization of risk alleles, the role of genetic mosaicism, and how germline variation informs our understanding of tumor biology. Dr. Chanik co-led the Cancer Genetic Markers of Susceptibility Project, co-chairs the BRCA Challenge, and has been a pioneer in identifying common inherited variants that influence cancer risk and outcomes. He also is medical director of Camp Fantastic, that does so much for our pediatric cancer patients at the NIH and others, and is a member of the National Academy of Medicine. And with that, I'll introduce our first speaker today, Dr. Pardis Sabeti, who will begin her talk. Thank you.
Great, thank you, Harry, so much for that lovely introduction, and I'm really pleased to be here with you all. Let me just share my screen. Give me one moment. Okay. Can everyone see that okay?
Yes.
Great. Okay, well, I have the pleasure to tell you about Sentinel. Sentinel is a locally led model for global pandemic prevention. Really, I'm really grateful for this opportunity to get to share the work that we're doing and to do this in a kind of a broad audience way to sort of walk you through a lot of the both the tools and technologies that we're building in scientific capacity, but also just a lot about the purpose and the work together. I just want to start by acknowledging my conflicts of interest. My lab and I have developed a number of technologies, and I've been involved in a number of companies related to diagnostics, sequencing, and AI, and licensed our technologies as well. And with that, let's begin. Well, as many of you are well aware, outbreaks are one of the greatest existential threats. They cause more death and devastation than most other crises in history. They hit the most vulnerable communities the hardest, and they go further, exposing and exploiting the deepest cracks in our society. During COVID, mental health declined, substance use escalated, education lagged. Children bear the brunt on so many levels. Outbreaks destabilize communities. They shake up governments. They deepen inequality. And the numbers are stark. The 2014 Ebola outbreak caused 11,000 deaths and $53 billion in economic loss. COVID-19 caused 7 million deaths and estimated 12.5 trillion in costs. Current U.S. global health cuts are estimated to lead to 15 million deaths over the next 10 years, including 4.5 million children. That's without a pandemic. And the chance of another pandemic has been estimated to be 1 in 4 in the next decade. The risks are only escalating with deep federal cuts in research, vaccine, and treatment programs for infectious disease, the closing of USAID. We have measles, polio, and TB cases rising, H5N1 continuing to spread and evolve. A novel form of Mpox virus circulated last summer, the virus closely related to Mpox. Over the summer, it was doubling every 2 weeks, going across all ages and genders. On top of all of this, we now have new technologies that allow any bad actor to modify these viruses to evade all of our defenses. We know outbreaks are a great existential threat. However, outbreaks are also solvable existential threats because today we have technologies skills and knowledge to detect pathogens and share information in real time to stop outbreaks. We can do this in many different settings, including remote rural areas. The same tools can not only stop a pandemic from happening, but they can also prevent and treat infectious diseases like malaria, tuberculosis, and flu in our communities. That's the underlying belief of Sentinel. Sentinel is a locally led system for stopping outbreaks within communities. It's based on 3 pillars. The first is the ability to detect both known and unknown pathogens in real time at different levels of the health system. That means from government hospitals to rural clinics and even in villages. Second, we need to connect this information in real time within the public health authorities and across the ecosystem. And this allows us to build a network that helps all stakeholders respond pragmatically. And third, and importantly, we then use this network to empower everyone impacted. Citizens can report their data. Frontline healthcare workers can have access to data and know what to do with it. Public health officials can make informed data-driven decisions. This helps protect the entire ecosystem from villages to cities, countries, and the continent from devastating outbreaks. We do this through a hub and spoke model. This central hub conducts core research and distributes information to spoke peripheral healthcare systems, even in hard to reach areas. This is the model that drives Sentinel. We put this hub and spoke model in practice in Nigeria and in Sierra Leone, and we've refined Sentinel over the past 20 years as we've worked side by side with local leaders and frontline responders in many public health emergencies, which you can see here on this timeline. And I'll tell you a little bit more about how we've applied the model successfully in a few of these instances and why we're working to scale now. So before walking through all of this, I want to show you an example of Sentinel in action, show you what empowerment is core to everything that we do. And I'll start by taking you back to one of the formative experiences that shaped Sentinel for us. As you may recall, that back in March of 2014, an Ebola outbreak was detected in southern Guinea, with 60 people identified in the region. At the time, we were supporting hemorrhagic fever centers in Sierra Leone and in Nigeria, working with national teams, and we had to brace ourselves and prepare for the likelihood that Ebola was going to spread to these countries. And this is members of my team on the right-hand side, Christian Anderson and Stephen Geyer, and on the left-hand side, Dr. Humar Khan in the blue shirt with our partners, Simbiri, Mambu, and Augustine, working really hand in hand. And here's the story of what happened. Well, the outbreak was detected in March of 2014 and actually believed to have started in late 2013 in a small village in Guinea with a toddler boy who had been playing around a tree inhabited by bats. And the boy became ill. He spread the illness to his family, and he and several members later died of Ebola. Over time, it spread through the community and through large parts of Guinea. By April, it was in large parts of Liberia. But when it entered Sierra Leone, it spread like wildfire. Something had changed in late May of 2014. And we can see it in the underlying data. So, the trajectory of the outbreak at that point had dramatically changed. As we sequenced the virus's genome and shared the data in real time, we began to see what was happening. The virus was mutating, generating hundreds of mutations in a very short period of time. This genomic data was important for many reasons. It allowed us to see the virus was transmitting from human to human, not environmental exposure had been believed. And it made public health leaders recognize the importance of hand washing and social distancing and contact tracing. As they began to encourage those practices, they were able to stop the epidemic from turning into a pandemic. As we studied the genome more closely, we discovered that some of the mutations we found in the virus improved its ability to infect human cells. This implication was stark. As the virus was having more opportunities to transmit from human to human than ever before, it was evolving to do so more readily. And I just want to note Jeremy Lubin and his group, who we worked with closely and who has been phenomenal in this regard. That's what happened in 2014 and how it went on to be one of the most devastating outbreaks, the most devastating outbreak of Ebola in recorded history. It killed more than 11,000 people, including our beloved colleague who served on the front lines. Those losses included our friend and close colleague, Dr. Shikumar Khan, who was with us in that original photo I shared. He was the head of the Lassa fever ward at Kenema. And amid this tragedy, we were actually on the precipice of a cataclysm. We were still breathing the death of our colleagues when my Sentinel partner, Christian Happy, received a call the night of July 20th. He was told that there was a suspected case of Ebola in Lagos, and we were asked to confirm it. He drove from his house down to the lab in the middle of the night, spent the night working on the sample from a suspected patient. By morning, he had confirmed the test. He called the public health authorities, then called me. This photo shows Christian and me sitting on the grounds of Redeemer's Church, just steps away from his lab, where he confirmed the first case. What was also going through our minds was the fact that the day after we confirmed the first case in Lagos, 3 million people were going to gather in that meeting hall for an annual prayer meeting. Christian had to end the call early to get out before the masses appeared, and the question it left us with was, what if it would have happened if even a single case of Ebola had moved through this crowd? Lagos is a city of 25 million people, and Nigeria is a country of 230 million, with trade and other connections all over the world. An Ebola outbreak could have wreaked devastating havoc and had a huge impact on the entire continent and the world. But the situation in Nigeria actually turned out to be very different from the rest of West Africa, because they had the tools, the knowledge, and the skills to address it in a way that was not done elsewhere. Very quickly, they confirmed the first case and worked with public health authorities. Within 7 days, we had the sequencing of the viral genome. We also tested hundreds to thousands of cases, sharing the data every time with public health authorities in Nigeria. By day 42, we saw the last case and then continued monitoring. By day 92, WHO declared Nigeria Ebola-free. In total, the team in Nigeria that we got an opportunity to be part of had only 20 cases, and with 8 losing their lives, we averted disaster not just for Nigeria, but for all of Africa and the world. This success was not the result of luck. It was because our work and partnerships made it possible, and the work that Nigeria had already done to set in motion a great public health system. It gave us the confidence that this type of approach could be a change in paradigm. Here you can see the difference between what happened between Nigeria and the rest of Africa. This taught us, and you can see that Nigerian, that small red in the corner. It taught us that applying a strategy could help us achieve 2 major things. First, the fact that we could actually detect viruses quickly and coordinate with public health authorities. And second, we could contain an outbreak and reduce the number of deaths dramatically. It laid the foundation for our program called Sentinel and gave us the inspiration to think about what we could achieve if we applied it further. To put it another way, the kind of system produces a significant return on investment. According to the WHO, every dollar invested, you'll get $5 to $7 in return on investment. And that brings us to Sentinel. This effort that Christian, Happy, and I led with our teams over the last, that has sort of been in its formation over the last 2 decades. We're going to begin with the technologies, then build the foundation across our pillars of detect, connect, and empower, and then take you through the other aspects of this. So as the experience in Ebola showed us, it was critical for us to create state-of-the-art capabilities to cut down the time and cost to respond to outbreaks. In Detect, we've been building powerful technologies to detect pathogens, including characterizing and identifying new ones. In our genomic centers, in our clinics, we have point-of-care sites in rural villages. We can test hundreds of viruses. All of these technologies are orders of magnitude cheaper and faster than other technologies and can scale and impact. This is what it looks like. We're also using artificial intelligence to improve diagnostic test design and speeding it up so new tests can be designed within a day. We've already proven this can work very, very well for CRISPR using both ML modeling and generative AI. We're also now applying it to PCR and LAMP-based testing. This is, in doing so, we're empowering not only our own technologies that we're building, but technologies across the ecosystem to support all partners in this effort. And those tools are being used in real time in outbreak response throughout West Africa. We also wanted to connect all this information in order to dramatically increase the ability to work quickly and respond. We didn't want just a few people to access and analyze the data. We wanted to empower the front lines. So we created Lookout, our flagship dashboard. This is basically, you can see it running right now, where you're looking at sequencing data being analyzed and case maps of what's going on the side. But this is essentially allows analyzing of sequencing data, identify cases, tracking spread, all on your laptop, anywhere in the world, even in the most remote setting. Lookout, this is all anonymized data. Lookout preserves privacy of patients while users have information they need when they need it. And you can see this is an example that we used on a college campus with Colorado Mesa University. They had very limited resources, but were able to use it very efficiently by having a good intelligence system to identify cases quickly. Underlying Lookout are a series of technological advances that we've made to enable us to democratize outbreak analysis. For example, there's something called Bayesian phylogenetics, which is the workhorse of outbreak analysis, allowing us to track and understand viral spread and evolution. We're able to move this forward to create we basically redesigned from scratch a Bayesian phylogenetic system that can work with orders of magnitude greater efficiency on a laptop anywhere in the world, giving you results within minutes. But, and usually only a few labs around the world can do that. And we really wanted to make sure that this was something, and this shows John Demby in our group running Mpox data in real time during the outbreak. We also recognize that AI is becoming foundational across nearly every field, but in biology, its potential is limited to a few labs with massive computational resources and massive resources to generate vast amounts of data. So we created our own AI architecture, tested it in more than 100 biological tasks, and found we could achieve and set the state-of-the-art performance at up to 270,000 times faster than other models. For example, identifying new viruses in a sample took one of the top labs in the world 30 days using over 500 GPUs. We did it in minutes on a laptop. So there's lots of technologies that I would love to share with you. I'm not going to, but our lab loves to publish and our work and get it out into the world. But fundamentally, I want to tell you a little bit more about what it looks like in action. Where does it have real public health impact? And so I'll take you through that timeline that I showed of how we began to develop the Sentinel system through basically a series of outbreaks, learning experiences along the way. And I'll just give you a few examples of some of those stories here. So our work really started in 2006 when Christian and I were both at Harvard and really started thinking about addressing viral hemorrhagic diseases. And one was Lassa fever. It was first reported in Nigeria in 1969, but in 2006, there's still no diagnostic in the whole country. Anytime there's an outbreak, 90% of the patients would die because the sample had to be sent out of country, and the result would come back 3 months later, and there weren't really working treatments available on the ground or diagnostics. Within 6 months, we brought the first diagnostic test of the virus to rural Nigeria, and soon after, we're joined in that effort by Bernard Noch in Germany. And the work together transformed not only patient care, but also reduced the patient case fatality rate. We saw changes from 90% to about 26% because the drug is, ribavirin is effective, but only within the first days of infection. So rapid diagnostic truly changes outcome. We also sequenced the virus, first whole genome of the virus, paving the way to the development of 2 major vaccines that are now being deployed in West Africa. I already also told you in 2014 Ebola outbreak, we advanced real-time genomic surveillance, showed how a Sentinel approach stopped the Nigerian outbreak in 92 days with only 20 cases and 8 deaths. Fast forward to November 2018, just 1 week in the southern part of Nigeria, there were 179 children that died of a mysterious disease. No one knew what was responsible. Viral tests for fevers proved to be negative. 22 samples were sent to Christian's lab, and within 72 hours, we identified the cause. It was a strain of yellow fever that had been seen in Nigeria for 90 years. It allowed us to, quickly work on public health strategies to stop the outbreak. It was, basically the data was immediately sent to the Nigeria Center for Disease Control. They declared an outbreak. Less than 2 weeks, it was contained, saving thousands of lives. So fundamentally, this idea of quick detection of the pathogen using genomic tools in addition to testing and rapid, well-targeted response by the Nigeria CDC. In 2020, COVID hit, and we all know about that. Egypt was the first country in Africa to report a case, followed by South Africa. Nigeria was the third. Within 48 hours of the suspected case, Nigeria had a full viral genome that we made openly available. It was the first SARS-CoV-2 genome sequence in the whole country. Sentinel then shared our protocols across the continent, directly supporting sequencing for 26 African countries and testing for more than 30 million people. This was a huge landmark for our Sentinel effort, and it just helped not just the Sentinel team, but also Africa come on board with this mission of coordinated work together. In 2024, Rwanda was battling a major outbreak of Marburg virus, and it was a truly terrible disease with a case fatality rate of about 80%. The Rwandan government called on Sentinel, and in partnership with them, we used the same approach, quick diagnostics, identifying hotspots through genomic sequencing, establishing transmission chains, and together we're able to contain the outbreak in just 66 days. The case fatality rate was only 20% in Rwanda, which was the lowest recorded. And earlier this year in Sierra Leone experienced an outbreak of Mpox that exploded this past summer with more than 4,000 cases reported. Our team jumped to action, worked closely with the Sierra Leone National Public Health Agency, identified a new variant that was responsible for the dramatic increase of the cases in the country. This new variant was doubling every 2 weeks. We also deployed our data visualization platform Lookout, and to help connect and analyze that data in real time. You can see this running on one of our initial small data set. Again, data anonymized, but everything available to the communities where they can look at individual cases, look at cases forming across the country over different time spans with full Bayesian phylogenetics running at the same time. This is now has become the 1-year anniversary of the NPHA. They showcase Lookout, having incorporated millions of data points over the last several years into the platform across lots of infectious diseases. It's now also being considered by the Africa CDC for a continental platform. And the final key aspect of our work is empowerment. So this is a quote we love. So when we applied for the 100 and change, we were pleased to have letters of support from all ministers of health of all 5 African countries that we were planning to work with, as well as the chief minister of Sierra Leone, with whom we are working to make a national surveillance program. And this quote says, at this pivotal moment in global health, Sentinel offers not only a powerful model for pandemic prevention, but also a path toward equity, scientific sovereignty, and leadership for Africa. And that's always been our intent in what we are doing. And we're grateful for the leadership of Minister Senga and many others in Sierra Leone, as well as across the continent. We felt the best way to sort of share our Empower programs is to just hear directly from the frontline responders that work in Sentinel. So I'll just take a moment. I realized I actually, in Microsoft Word, I don't know if you can hear the sound, so somebody just call out if you cannot.
Majority of our research participants, Sentinel was a lifesaver because it was their first and most likely only experience with a place that would give quick, free, and accurate diagnostics.
I would say this Sentinel study actually had a huge impact for us. Sentinel is the largest surveillance project that we carried on as a site, and this was quite huge in terms of capacity building. Our sites and our study team were exposed to research skills.
We've done some incredible science together, but what mattered most to me is how deeply they have invested in me. With their support, I earned my master's degree at Harvard University. To me, Sentinel isn't just about changing the world. It's about changing lives.
I see Sentinel to be very different from the other outbreak prevention system because Sentinel is a proactive approach that involves regular collection of blood samples. And those samples have been tested for high priority diseases that we know presents a significant threat to public health.
The Sentinel sample collections, this one was an idea that was welcomed by the hospital and the entire community. We had the community engagement, the stakeholder engagement. Everyone was happy being part of that process.
In Sierra Leone, Sentinel has been and is a critical part of science development, specifically with regards to diagnostics.
Sentinel also strengthening our collaboration with the National Public Health Agency and the Ministry of Health in Sierra Leone. And this was recently demonstrated during the Mpox outbreak. Our lab was used as first responders. We were tasked on the genomic sequencing, on which we are still leading.
In a country whereby people find it very difficult to afford basic health care, having a program where they could get diagnostics for free and at a very fast return rate was very important.
We are looking forward to improve our capacity and to resolve health issues not only in Nigeria, but our findings will also be helpful to people in other parts of the world.
So our education journey began in 2007 when Christian and I were launching our Lassa fever program in rural Nigeria. We recognized the extensive exchange across education between countries would be critical to our success. And with support from the World Bank and the NIH H3 Africa program, in 2013, we were able to expand training access in the ensuing raise. We began through summer-long programs at Harvard University and the Broad Institute in genomics and diagnostics. We continued this over several years. We always recognized we wanted to move the center of gravity to Africa, and from there could have much more impact. We ran it over several years, and as the Institute of Global Health, Genomics and Global Health at Redeemers was established in Nigeria, Christian and the team were able to expand our education efforts further and further across the continent. And with COVID, they jumped to action to accelerate this at a high level with numerous bootcamp training programs at IGH and on-site trips by his team to countries. Sentinel has now trained over 3,000 frontline responders in 53 of the 54 African countries, and together sequenced tens of thousands of genomes along the way. In addition to education, we believe it's essential to build infrastructure and specifically that are in and specifically designed for the regions most effective. I would welcome anyone from the NIH to go and visit us in Nigeria and to see the new center that we built there at the Institute for Genomics and Global Health, and we are always welcome. But in lieu of not being able to see it in person, here's just a video from the conference where we launched the site with the Minister of Health leading the opening.
To look back at the tremendous impact that the center has had in Nigeria over this last 10 years.
I think we're very proud of the accomplishment of the Redeemers University.
It's unimaginable.
Our Father and our God, we say thank you. We ask that you perfect all that concerns this meeting. And we ask that at the end, your name will be glorified. In Jesus' name, we have prayed.
I would like to extend my warmest greetings and heartfelt welcome to all of you. Your presence here today signifies our shared dedication to promoting scientific innovation and research.
And someday we want to see vaccines being produced here by Africans for Africans.
I think it's great to see the tremendous strides, and Professor Christian, happy your team, the leadership of Redeemers University, the past leaders, the current leaders, and your exemplary team. I think you've done an amazing job. You did it. I think you should be commended for that. So thank you for all the hard work.
In the sense of the community, the creativity, the science, the love and care that's been put into every aspect of everything that we experience.
So that's our Sentinel program, and we've pressure tested and demonstrated its capacity in this hub and spoke model to powerfully stop outbreaks, preserve lives in Nigeria and other West African countries. We've along the way learned a lot and had great results and had opportunities to support other countries. You can see here the many sites that we're including in Nigeria, as we recently won the MacArthur 100 and Change Prize, and we're very extremely humbled and grateful for that opportunity, especially in a time like now, to be able to continue the work that we're doing and show evidence of this model of working with local communities can be impactful. And through the MacArthur, we're aiming to scale this in West and Central Africa to have either greater impact using that same hub and spoke model. We'll have major hubs, then go remote, hard to reach areas across the countries. This includes now Sierra Leone and Nigeria, but new Sentinel countries in the Democratic Republic of Congo, Rwanda, and Senegal. Ultimately, I believe this model can be implemented throughout Africa and beyond. And we've already worked with governments of DRC, Senegal, and Rwanda. We've worked with ministries of health, national public health institutions, and we're grateful for their support in the effort. We also work with regional and global health organizations like the WHO, Africa CDC, US CDC, and of course the NIH, which has been instrumental in every aspect of the work we do, and a real leader. And we don't work in isolation, we work and cooperate in our aim to be flexible always, dedicated to strengthening not just national health systems, but the global health system. So ultimately, why do we care about these issues now? Well, the global investment in public health and foreign aid funding has been decimated. We all understand the consequences of that. Infectious disease outbreaks are rising, the risks are accelerating. WHO says in the past 10 years, the risk of outbreaks across the world has increased by 20%. And we see that impact now. We believe strongly that advances in technology and our track record as a community of scientists and advances in AI really truly provide a unique moment and an opportunity. And we hope to be part of that with our Sentinel effort, working with lots of tremendous partners across this entire global health ecosystem. We also recognize, again, this opportunity that we've been given, and to us, it's really important to figure out how we can use that to lift all boats as best as we can. We know the consequences that it has for Africa, where we work closely, but for the US and the world. And why do we believe in Sentinel? For us, it's more than just an early warning system. It's a model that's more about than stopping disease and protecting life, but it's really more about empowering people, equipping them with the tools, the systems, the knowledge to create strong and resilient communities for generations to come. And our aim is not just to prevent children from dying of preventable diseases, it's to ensure those same children grow up leading the world in science and the systems that protect us all. For us, we aim Sentinel to become a model to help stop outbreaks before they spread, and for taking on humanity's biggest challenges, locally owned, globally relevant, and built to last. And then I'll just leave you with one last thing about outbreaks. I think, I hope you leave not just knowing what an important but also solvable existential threat outbreaks pose. But there's one more aspect of why outbreaks are such a unique existential threat. It's that they can only be solved together. Unlike other existential threats, every person's actions truly make a difference. Because of the exponential spread of infectious diseases, one missed case can start a pandemic, and that means every person can help stop it. That's why we created Sentinel, to put state-of-the-art tools in the hands of frontline workers and everyday citizens. It's a locally led system that empowers communities to protect themselves, and in doing so, prevent the next pandemic. Outbreaks are a shared threat that brings us together. Sentinel is about partnership, solidarity, and hope as much as it is about the technologies around it. And I'll leave you with an experience, again, from our Ebola outbreak, where we started. It was that moment when Dr. Khan had passed away of Ebola in July of 2014, and Christian had called me just days later, having diagnosed Ebola in Lagos, Nigeria, a city of 20 million. At the time, I was with 21 of our West African colleagues who were spending the summer training with us at Harvard, preparing to join them on the front lines. As you can imagine, it was one of the worst moments in a very difficult job that we do, and everyone was devastated. But we gathered there to do something we always did on Sundays, which is to sing. And though we didn't know where to begin that day or why to sing in that moment, words sprang up then and there during a session that formed a song called One Truth that has become a sort of anthem for what our purpose. So I'm going to play you a clip from that song. So you'll see it'll be odd because, again, this is just the 2 nights before. You'll see the first night, and then I dragged them back out the next night, right before they left for to go to their home countries to help stop the Ebola outbreak. But I felt in that moment I really wanted to film this, and I'm glad I captured that moment. You'll see it's filmed outside of the Harvard Science Center the night before the teams returned to the front lines. And what I hope you'll see is hope, joy, and amazing resilience and togetherness, which is what we truly needed at that moment and in that fight. Thank you.
Thank you for that wonderful presentation describing how you married epidemiology, hard science, and the critical social interactions of the communities that you've brought together and serve, and that serve themselves. So we'll hold on questions now, and we'll bring up questions at the end of Dr. Chennick's talk. Thank you so very much. We'll move on now to Dr. Chennick, who will tell us a very interesting story about his work with radiation exposure. Thank you.
All right. Harry, I assume I can be seen. I want to, first of all, thank the organizers for inviting me to speak at this Demystifying Medicine. And I'm going to be focused on demystifying risk and demystifying ionizing radiation. And it's a very important public health issue, one that everyone worries about, much as Pardis's absolutely fantastic talk that we just heard about infectious diseases and outbreaks, really quite inspiring and quite remarkable. I unfortunately don't have the same kinds of videos and things because this is complicated in different ways. But I want to talk about how ionizing radiation informs our understanding of radiation-related cancers and lessons learned from the investigation of the aftermath of the tragic Chernobyl accident. So we all know about ionizing radiation. We know exposures to humans can occur in many different ways across a wide spectrum. This is where knowing what the actual exposure is and how long and the isotopes is very important. Living near a nuclear power plant and having dental imaging is very different than receiving radiotherapy for, that very important decision to treat a progressive cancer per se, or cardiac catheterization, or whole body CTs, head CTs. Somewhere in the middle, as you can see, there's a spectrum, and the risk is related to the dose, not only in the total amount and the way in which it's given. So I'm going to spend most of my time today talking about ionizing radiation, which we know causes cancer. The International Agency for Research in Cancer and its monographs have classified it as a class 1 carcinogen. It's just something we've known, but the classification was very important. It's a risk factor for multiple cancers, which I'll talk about. And again, dose really matters. There's a tremendous amount of data in the literature on animal studies with high exposure causing double-stranded DNA breakage, and supposedly the shibboleth is that a clean-cut damage, there are 20 events for every gray of exposure. So as you see in the red box, really the three main questions that I'm going to address today. Exactly how does it cause cancer in humans, when, where, and how? With exposed parents, is there a transgenerational risk to children? This is not only important in Chernobyl, but in Fukushima and other places where there may be radiation exposures. And does the low to moderate dose of ionizing radiation induce biomarkers? These are three questions that we can learn and be informed by what has been a huge investment on the part of the international community, and particularly the NCI, in working with colleagues in the Ukraine and in Belarus and Japan, following the individuals who survived the atomic blasts in Hiroshima and Nagasaki. So ionizing radiation does indeed increase cancer risk. We know following the atomic bomb survivors, we can see the solid cancer incidence increase over a period of time. Solid cancer mortality after occupational radiation exposure clearly is there in small amounts. These are very of different degrees. Brain tumor risk after head CT in childhood is extremely small, but there, and a lot of discussion about that. And increased cancer risk after radiotherapy for children with cancer, who then develop, as you can see on the right, a range of different cancers, and thyroid being one of the more common ones that's seen in children who've received craniospinal or cranial radiation. So where and how do we learn about the risks and consequences of ionizing radiation with respect to cancer? Well, medical exposures, as I mentioned, both diagnostic, therapeutic, and occupational exposures. Environmental exposures, unanticipated release, atomic blasts and nuclear testing, background radiation such as radon, and animal cell and cultural studies. I'm going to particularly today focus on a very remarkable opportunity that we've had to be able to study radiation and its effects in the aftermath of the Chernobyl accident, where we know exactly discretely how much radiation was spread over what period of time, who was there, and what both their risks and those that developed it, what do those cancers look like? So we all know that accidents happen, and iodine 131 release is a very important measure of the nuclear industry and of atomic blasts. And we measure the release in bevacles times 10 to the minus 15th per second. So after Chernobyl, it was roughly 1,800. After Fukushima, it's literally less than a tenth of that. And something that we all are familiar in this area from years ago, the 3 Mile Island, was orders of magnitude smaller in terms of the radiation exposure. Similarities, we know that they all had types of released radiation of I-131. There was extensive exposure to workers and the general population. The risk perception was high, and the perception was unrelated to dose. Any radiation was considered to be dangerous. I'm not arguing that there's good radiation in the environment. There is good radiation for therapeutic purposes, and we made allusion to that, and we'll come back to that a little bit later. But there were delays in effective communication of public health messages. So we need to understand more about this and be able to communicate better with the community. And the health effects are probably most substantially in number and intensity mental or, anguish. The physical things, I'm going to talk about cancer, but also cataracts and cardiovascular are clearly important consequences of environmental radiation exposure. So the Chernobyl nuclear power plant accident occurred early the morning of April 26th when reactor 4 blew, and the resulting open-air reactor core fire contained 9 days later. Some of our colleagues who were in the health physicists and dosimetrists have spent their careers mapping the radioactive fallout, particularly looking at I-131, which I will highlight why that's so, and seeing that really this is a map of the Ukraine, but the Belarus, just above it where that symbol is, was very heavily hit, and parts of Russia. Now, as the meters went off in Sweden and Germany several days later, those levels were orders of magnitude smaller. And as we all know, it took several days for the Soviet authorities to publicly acknowledge and to move on an appropriate response. So here is sort of the radiation map that we're used to seeing in our world, looking at where it really settled due to all of the, the weather conditions and the like. And we really have two different cohorts epidemiologically that have been developed over the years. The residential exposure from fallout, where thyroid cancer was particularly a problem, and I'll focus on that in a little bit. And as you can see, areas here of Belarus and certainly in the Ukraine and much less so in Russia certainly had extensive exposure. And then there's the occupational exposure of the so-called liquidators, the people that came in to do the cleanup, the conscripts who primarily were, military conscripts who were sent in to do the cleanup, often with insufficient or inadequate protection, much less guidance as to what to do to protect themselves per se. So we, over the years, have been very involved with Ukrainian, Belarusian authorities and scientists for these two sets of kinds of cohorts. And I will make reference to both the residential exposures when we talk about thyroid cancer and the occupational exposures, particularly when we talk about the transgenerational effect, because these people were there for a discrete period of time. We know exactly how much exposure they had, and then they leave and some start families, and that's been a remarkable opportunity. So just everyone always knows and has seen the HBO series, and people have talked about this, the immediate effects and the extremely high exposure in plant workers. Anecdotally, were clearly there. 2 plant workers died in the immediate aftermath. There are 134 registered plant and emergency response personnel who suffered acute radiation syndrome. 28 were fatal in near term due to nausea, vomiting, bone marrow damage. Many were taken to Moscow, and Americans and others from around the world came and tried bone marrow transplant, but it was unfortunately too late and insufficient at that time. We also know that there was no national tumor registry nor real medical system for follow-up. This was 1986, towards the end of the Soviet system, when a number of the social systems were breaking down, and that's particularly important for both information and for medical care and also for nutrition. We also saw a small series of case reports after Chernobyl of children with thyroid cancer drawn from Ukraine and Belarus, where samples were brought out, and the preliminary evidence increased a frequency of certain kinds of fusions in the red gene with very few point mutations. And the rationale was here really set down in seeing these small little case series suggesting that the radiation caused some or all of the thyroid cancer. And an important question that we wanted to answer is what fraction and how and what do we learn from this that really tells us what's a cancer that's been really driven or determined by radiation exposure, as opposed to what is a sporadic cancer that may have already been going along, and does radiation either accelerate or slow down that growth? The latter question is very hard to do. But we built this on long-term investments of epidemiologic and screening cohorts, and particularly I'm going to focus on the Ukrainians. We've learned a lot of information from Belarus, but we are not allowed, and we've never had biospecimens be brought out of that. The dosimetry is something that's gone on for almost 40 years now, of experts who continue to refine the analyses. And then the introduction of the integration of genomic technologies and the success of TCGA in 2010, 11, 12 really, spurred and stimulated the interest in that. I got very interested at that point in wanting to apply to a very discrete, well-described group of individuals who we knew exactly how much radiation they were exposed to, when, where, and what type, and could we begin to map, how that relationship really went forward. So I'd shown these slides before of the solid tumors, and the question is really, what's the genomics? Are some people genetically susceptible to radiation-induced cancers? When in the carcinogenic process does radiation have an impact? Does it contribute to more aggressive cancers? And is there a biomarker or set of biomarkers for radiation-induced cancer? These are pressing issues, multiple meetings we've been to, and a number of us have talked and been part of with UNSCEAR, NCRP, and certainly the National Academies, who the National Academy runs co-runs the Japanese organization RARF, which follows the survivors of the atomic blasts in Hiroshima and Nagasaki. These are really very tragic events that are our opportunity to learn about radiation risk per se in the population. So today I'm going to talk about the second, third, and fourth, but the germline, which is interesting to me, we just don't have the numbers to be able to make informed decisions. So again, going back to the accident and the spread, what was interesting was reported was over time, epidemiologically, we could see that the younger you were at the time of exposure, the greater your risk of developing thyroid cancer. And this is also been seen in external beam radiotherapy and in the atomic bomb survivors. And what was particularly important in the Ukraine was this was an iodine deficient diet for many of the kids. So contaminated I-131 would be taken up with even greater avidity and be concentrated even more in the thyroid gland. So the papillary thyroid cancer is the most common one that we see. It's a higher incidence in women, 3 to 1, with 95% survival in the West. It's a cancer of young adults, highly differentiated. We know from TCGA that the mutational burden is higher in older patients, suggesting it takes longer to develop. But also we know it's very restricted in the types of mutations that are responsible for really being drivers. It's actually what's so remarkable is it's really singular. just one particular mutation can drive this, and then it changes the whole pattern of the thyroid. So when we go back to this model of the release of I-131, it spreads over the over the residential areas and contaminates the grasslands where the cows feed. And this is, again, I emphasize the Ukraine 1986, where the nutritional sources for young kids were quite restricted, and milk from those cows was a critical element in their nutrition. So a lot of the younger kids drank a tremendous amount and at high doses from the pasture cow milk axis, and the iodine deficiency in the contaminated areas led to increased uptake. So at the same time, now that we had these epidemiologic advances, Jerry Thomas in London, now retired, a marvelous pathologist, with Mikolo Tronko and Tatiana Bogdanova in Ukraine at the IEM, had set up the Chernobyl Tissue Bank. And this is a bank of tumors that were all either identified by screening or clinically treated in the same institution, IEM, with the same handful of surgeons, having their thyroid removed in according to very standard modern practices, and then 6 different pathologists from around the world agreeing on the diagnosis of papillary thyroid carcinoma. So this is really, if you don't mind my saying, getting it right. So again, we capitalized on the epidemiology and clinical data that went with this, the dosimetry, and then now applying modern genomic analysis based on things that we've learned from TCGA, ICGC, PCOG, and the like. So we published a couple of years ago, led by Lindsay Morton, the director of our radiation epidemiology branch, 440 individuals who had fresh frozen pathologically confirmed PTCs. High quality data from whole genome sequencing and mRNA sequencing and methylation with matched normal. And some of them we had trios where we had blood, we had non-tumor thyroid from the other side of the thyroid that was removed, as well as the tumor as it was removed, reviewed pathologically, and then put through basically the same pipeline that had been developed for TCGA. And we also had a number of cervical lymph nodes, 47, from some of those same individuals. And as you can see, we subsequently published on those, and I'll mention those. So our landscape analysis really had 68 primary variables, and we had marvelous colleagues at the Broad, Gaddy Getz and Chip Stewart, and in our own hands with Eric Dawson and Danielle Cariati, Steve Hartley, and others, to really look at the whole genome RNA, microRNA, SNP array, methylation, telomere lengths, and have these 68 primary variables that we then crossed against the clinical and the epidemiologic information that we had. So we saw in the Chernobyl, almost all the tumors had a candidate driver, whereas in TCGA, they only explained 75%, we had 98%, and the majority had a single driver, and almost 94% of those were in the MAP kinase pathway. So there were a large number of known single point mutations in BRAF and the RAS genes, and then a small handful of tumor suppressors. We didn't see anything in the germline that in any way correlated or predicted these, but we saw a plethora of fusion drivers with RET and NTRK3. These are well known in thyroid cancer. We know that the fusions can have a higher frequency in younger individuals, but not at the level that we saw in this Chernobyl cohort. So the PTC drivers, there was a major shift in the number and the fusions with respect to radiation exposure, because we had exposure everything from just a few milligray to well over a gray, to be able to map this and to be able to say, all right, see excess odds ratio, what's that 1 plus 0.93? So it increases with increasing radiation exposure. There are clonal events, that means just one particular driver that's particularly with fusions that's simple and balanced, and we can clearly see the hallmarks with our colleagues of non-homologous end joining, one of the several different kinds of DNA repairs. We also saw that they had very low mutation background, so it's not as if radiation was hitting in many places. A single clonal driver, and with thyroid, it's really the single bad hit at the wrong time. Okay, there were many children who were exposed but didn't receive or didn't develop this. So if we sort of take a recap of how we've gone our progression going from the exposure, the double strand breaks, the thyroid cancer that then develops, the genomic landscape analysis, to really focusing on what the relationship between radiation dose and double strand breaks, and particularly the importance of the fusion. But we also know that there were other things. There were small deletion counts. There were certain signatures that we could see. These are the kinds of things that we now use in cancer genomics to try and map both endogenous, in other words, problems that come out of DNA replication, as well as exogenous exposures, which there are certain signatures we know that are characteristic for cigarette smokers or UV light, but we didn't see any of those. But what was interesting, we did not see any signature for radiation itself. So we saw primarily simple, balanced structural variants. And this is very important, which we then said, all right, if we look at the radiation influence of the characteristics of metastases in those 47, we could see, as you can see, each of these sort of double plots here, that what we could see really is that the primary and the tumor looked almost identical. We could not put our finger on something that caused the metastasis on its own per se. There's some interesting expression data with the HOXC set, but that's a story still to be told. So we didn't see a direct effect of of radiation causing metastases. We also know that metastases are more common with fusions than with point mutations. So it's not surprising that we saw lymph node metastases in individuals who had the fusions. And we saw more fusions in the radiation set than in those who received radiation. We had some 81 individuals who had no radiation, who we identified and recruited shortly after the end of the time period in nearby areas. So the fact that we saw more frequent metastases in tumors with fusions, we know that radiation is indirectly responsible for that. We didn't see any radiation signatures in the metastases themselves, and there were no other patient or clinical or tumor molecular characteristics associated with radiation with the lymph nodes. So again, this was a set of patients who were operated in the exact same institution by just a handful of surgeons, followed according to a well-established clinical protocols. So this was really an extremely scrupulously followed group of individuals. So now with this information, we were then asking the question, can we distinguish which thyroid cancer is driven by ionizing radiation? Because not all of them. We saw some of the point mutations, and we saw some complicated fusions. We know that so far we've been unable to identify a single biomarker that's identified in DNA, RNA, or methylation that says radiation damage or not radiation damage. Sets of biomarkers can indicate a strong probability of radiation-induced. So the simple fusion drivers with two breaks that come together and a very small space in between as it gets broken and very quickly repaired by non-homologous end joining. Fast, efficient double-strand DNA repair in otherwise healthy cells, leading to some small deletions due to the double-strand breaks that you can see in the background. The point mutations and complex fusions really are unlikely to be radiation related, and we could use the clock signatures, other things that other biomarkers we have to date the start of those tumors to other points in time that didn't really map to the 1986 range per se. Because we know that in the background there is a rate of papillary thyroid cancer that occurs in young children and young adults. And we have no real tumor registry at a national level in the Ukraine until much later. The other thing that's interesting is the driver shapes the expression and the epigenetic profile. We are yet to put our hands on a whole set of radiation changes. So once it becomes a cancer, the cancer driver in the MAP kinase clearly drives what the characteristics of the tumor look like. So we have some insights into the thyroid carcinogenesis from this and insights into radiation-induced tumors, seeing the very clean, simple, single-balanced fusions that are generated and the small deletions around them. And the question is there a complex signature? Yes, we think there is a complex one, and that means we have to do extensive analysis. You don't just do a single test to say, was this a radiation-induced one or not? Does the profiling suggest therapeutic steps? That's a very good question. And this is all, in our minds, very important because a number of the cases, even with these simple fusions, had lower doses of radiation, well below a gray. And for the public at large, this particular figure on the lower right is really important. And there's a lot of debate about what happens, is it linear or does it increase the risk of certain things or decrease with the so-called hormesis, that a little bit of radiation may be good. So as we continue our analyses, and we are now basically doubling the number of individuals that we're able to study, as we have new sets of cases that we're analyzing and related tumors and follicular carcinoma of the thyroid, to try and better answer and understand what these low doses may or may not mean with respect to risk for individuals. Because this is the space that most of us live in and worry about with respect to not only thyroid, but other cancers. I think that we don't have well-characterized cohorts of individuals following other kinds of radiation exposures that allow us to really see those signatures. Some of the recent lung cancer work certainly, has tried to look at radon in lung cancer, which epidemiologically has been linked, but we can't see the genomic signatures in that. So now I'm going to just shift gears for a minute and talk about a long-standing controversy over possible transgenerational effect to radiation. There's been a lot of animal data, some in the civilian literature and some in the military literature, that look at structural and chromosomal events. Those are the kinds of things that are used in the nuclear regulatory industry to follow and test and screen individuals who have higher doses over extended periods of time. But in humans, very low or protracted doses really are not well studied. There's some small underpowered studies of a handful of genetic markers that came out after the accident where people thought a few microsatellites may be increased or decreased. Those are combination of chance and issues related to publication bias, in our opinion. The structural and chromosomal events, as I said, used for monitoring nuclear workers is very important. But again, the nuclear industry is very good at monitoring how much exposure, but what the biomarkers are that really are important to change people's positions or to retire them is still a complex science. So we wanted to ask this question: is there a transgenerational effect of protracted radiation? So we turned to asking this question of de novo variants in adult children born to the second cohort that I mentioned, the liquidators and evacuees. So we have a family structure design that we set up in the liquidators, where our first published, and now we've increased this, where we have 105 families where the father and or mother were liquidators. We know exactly how long they were there, how much radiation exposure they had. They leave. Remember, it's 1986 and 1987, they start a family, and anywhere between 87 and 2002, they have one or more children. We did very high coverage whole genome short read sequencing, twice the normal because we didn't want to miss things, looking for new variants were generated in what we call the de novo variants at conception itself. And this is built on a cohort that we had set up with our colleagues in the who followed the liquidators, Dmitry Bazika. And this is an essential, so to speak, type of variant because due to random mutations in gametes, sperm and oocytes, there are a number of variants that are generated by classical pipeline every single conception, and they're usually between 40 and 100 that increase with age of the parents, the father more than the mother, at the time of conception. These newly appearing variants are known as de novo variants. They used to be de novo mutations, mainly because the bias of finding them in settings where there'd be catastrophic or significant genetic diseases and seeing neither a mother or father with it, but the child having that mutation. This is as dropping down to the bottom, certainly explains some of the pediatric developmental diseases, and certainly autism has been very interested in this. Is the older the age of the father, the greater the likelihood of some mutational events that may be very important for underlying that neurodiversity condition. It's a critical step in evolution. This is how new variants are introduced and then can be either selected or deleted. And they're seen only in the child, but not the parent. So it's an arduous fact to do this. So we look for these things that we know when we classically sequence the mother, father, and child with whole genome sequencing. We can see a variant in the mother, for instance, and then we see that in the child. That's the majority of variants. Every so often, you see something in the mother, you don't see it in the and you see it in the child, but you then see something that you see in neither the mother nor the father. And there's a intense quality assessment that needs to follow that you go from thousands of those potential sequencing artifacts to a handful. And we actually hand curated and looked at all the ones that we're reporting. So the estimated cumulative radiation dose, so we knew from the mother and father exactly how much radiation they had. And the fathers were in categories that were much higher doses than the mothers. So we could look at the maternal and paternal doses, looking at different types of mutational events, whether they were clusters or complexes, or whether they were insertions and deletions, microsatellites, a single nucleotide, and then what the total was. And when we went and looked at this, we could not see any effect of radiation to the parents. And this is a very important question, because maternally, most eggs are there when a young girl is born, and potential mothers have them through their lives, whereas sperm is generated in the external compartment, so to speak, of the testes throughout someone's life. Granted, there are stem cells that are important for that, but it is a very, it's a higher risk for events. And we were able to look at parental age and parental smoking status as well. So when we did a whole series of sophisticated analyses looking at the age, conception, particularly of the parents, the father jumped off the page, and that's what we fully expected. In about 42%, we can assign with adjacent variants the paternal origin, and seeing about a 4-to-1 father to mother range in that. When we looked at cumulative radiation dose, when we looked at smoking, we could not see any effect. When we compared what we saw in terms of the distribution to the decode set and the Danish and other American sets, we saw that the distribution of the types of mutation were identical, were not different in any material way. This was work led by Meredith Yeager. So we could evaluate, the peripheral blood of adult children conceived years afterwards. So we know there's a survivor bias. We are not able to investigate men and women who had very high doses in the immediate aftermath. Many of the, a small fraction of those liquidators were very sick, as we mentioned, and some of them died or had acute radiation sickness and were had other conditions, so that starting a family was not possible. We use short read sequencing technology, and we're going a little bit deeper with PacBio, but this is important to consider these. So our transgenerational study really shows that if there is a risk of deleterious DNVs, it's very small, if at all, and it's very anecdotal. It's not a repeated or a frequent event. We saw adequate power to identify substantive increases in DNMs in adult children born to liquidators and evacuees, again, knowing that there's a survivor bias there. No increase in DNVs observed due to radiation, and no epigenetic signatures. The doses were low and extended, more so than we've seen in animal studies, so a lower rate of gonadal DNV events. And this is something that's been debated back and forth, and our reviewers, and certainly subsequently at meetings, altering the balance between new DNVs and DNA repair in the lower dose may actually be so. Now, the public health implications, when we published this in 2021, were very important. I got flooded with a request to speak to Japanese media because the return of individuals after the 2011 Fukushima accident was still a problem. And one of the major reasons people were unwilling to return to Fukushima was the risk of individuals of childbearing age. Were they going to have a series of mutations that may lead to problems with their children? The timing of the radiation dose is certainly critical, and we are continuing. We have more Chernobyl families with high and medium doses, and we see no change in those. Those are getting ready to be published. The famed Brazilian accident in Guyana of the cesium-137 that literally fell off the back of the truck. In those families, we've sequenced and see nothing. And it's taken a long time, but close collaboration with the Japanese, we now have in progress 580 families where the mother and or father were exposed and their children, and doing the same kind of high definition sequencing, particularly asking the question of pre and post pubertal expression differences for the fathers. Again, these are important public health implications in thinking about how and in what way we address this question of low dose. Is it a linear? Is it increased, or is it decreased due to radiation? There's a raging debate on this. Okay. So the last thing I want to just briefly talk about is, are there biomarkers that we could see in the Chernobyl setting? So clonal hematopoiesis is something that's sort of come on in the last 10 years. Alternative clones in the bloodstream that are somatic mutations that are selected, and we know they're common with aging. We know they're increased for risk for hematologic cancers, particularly, as risk factors for both chronic and acute leukemias and other hematologic states. They can be driven by exposures. And one of the things, a colleague, a former graduate student of mine, Kelly Bolton and Lindsay Morton and others, published not so long ago, that cancer therapy can shape the fitness landscape of clonal hematopoiesis. So looking from a large cohort of individuals at the Memorial Sloan Kettering, the increase in CHIP, that's clonal hematopoiesis of indeterminate potential, most commonly affected, they're these genes, DNMT3A, AXL1, TET2, and P53, that are by far the most common genes. And this showed that the risk is much higher with radiotherapy exposure, but it's also seen with chemotherapy. And can the red marrow radiation exposure from other sources and across a non-therapeutic dose range, including low dose exposure, increase the risk of CHIP? So that's the question that we then went back to our liquidators, where we had 290 families that we recruited, where we could ask this question of low to moderate exposures, that do they increase the risk of clonal hematopoiesis? So we could look at the radioactive release and ask the question, doing the dosimetry for red marrow exposure as opposed to thyroid exposure, which we had done in the thyroid cancer studies, knowing that those are different. That's, our dosimetry colleagues are experts in those discriminations. Looking at radiation-induced damage that may lead to increase in clonal hematopoiesis. So when we looked at our 290 trios, the parents as well as the children, the fathers had by far the most radiation exposure. We saw the class and types of mutations were exactly what we would have expected in the general population. And so when we ran this against radiation exposure, we did not see the low to moderate dose radiation increasing the likelihood of clonal hematopoiesis. So there was no evidence for increase in the incidence of clonal hematopoiesis. This study is going on. We'll have larger numbers. We could very well have missed a small, low signal for specifically the low or moderate doses in fathers, less so in mothers, and certainly nothing in the children so far. We didn't see any evidence for new genes involved in CH. We know there are a whole set of radiation-related genes that can be either induced or important in response to radiation, and we focused on many of those and didn't see clonal hematopoiesis popping up in those per se. So really, in wrapping up, we see these genomic studies as very helpful in understanding, reassuring in some situations, understanding and identifying aspects that are very important in understanding carcinogenesis and decisions that may be made that could have therapeutic implications, but that we're not able to study following the Chernobyl. And then certainly, are there biomarkers that are out there? And the response, this is important to know these the answers to these, because there could be future nuclear accidents, and this informs radiation protection standards in workers throughout the world, and identifying particularly susceptible populations for prevention and follow-up, and also giving us very important insights into carcinogenesis, which could have therapeutic and preventive strategies down the road. And as you know, many different organizations across the world, from our colleagues in the Ukraine, Belarus, and elsewhere, as well as in the United States, are really focused on these questions. So I really need to call out the marvelous people who have been doing this for decades, and particularly our three colleagues in the Ukraine, Mikhailo Tronko and Tatiana Bogdanova at the IEM. That's where the thyroid work was done, and Dmitry Bazika, who oversees the liquidators. And there's a long, marvelous history in DCG, that's the Division of Cancer Epidemiology and Genetics, here in the NCI, where work has gone on, and particularly I highlighted a number of things published and led by Lindsay Morton, the current branch director, who's really been marvelous in really marrying epidemiology and genomics and dosimetry. So for the first part, this is a large team effort. As you can see, people from around the world and many different universities, both in the U.S., Europe, and certainly our colleagues in the Ukraine, and certainly for the transgenerational and clonal hematopoiesis. You can see, again, many wonderful people here on the stateside, certainly, but also in Japan, and particularly in Ukraine, who are our colleagues who we stand with and work closely with and communicate with regularly. So with that, I end and say, the Division of Cancer Epidemiology, we have 110 fellows and trainees at any one time, a wonderful place to study many different things that are important in cancer epidemiology. And with that, I will bring my talk to a close. Thank you, Harry.
Thank you, Dr. Chanik. That was just a wonderful talk and a very interesting review of what we know about the kinds of radiation exposures that you described today. I think what I'll do is, since you just finished your talk, I'm going to focus first on a few questions for you, and then I have a few questions for Dr. Sabetti. So one of the things that comes up from this is at the very beginning, you presented some important slides talking about long-term effects of low-dose radiation and the cancer risks. And yet you had such a difficult time, even with high radiation dosing, to find markers, except in the children, that match that. And so clearly, this is an ongoing issue. And I guess my question is, could you expand on, I guess, what we still don't know versus what we know about low-dose radiation? Because everybody's going to worry about, what about the radon in my cellar, and what's the risk to me, and things like that.
Well, absolutely, the risk of having a CT, as you see these papers in the New England Journal of Medicine and elsewhere, the risks for hematopoietic or solid tumors, they're there. The absolute risks are very small. And this is, I'm going to answer your question in a second, but I want to step on to the public health soapbox for a minute, that we have to look at what the absolute risk of these things are as opposed to the relative risk. Because you say radiation and everybody raises their hand and says, oh my God, this is terrible, I want no radiation. So what the absolute risks are very small for these low dose. And there are some that argue that very low dose can actually be beneficial. That's the whole world of hormesis. And that's mainly driven by cellular and models per se. Epidemiologically, we don't see that. We don't see a survival benefit for that. When we get to what the exposures are, we have the other extreme, which I didn't talk about. Lindsay and others are expert in it. When you get high dose radiation for cancer therapy, what is your risk of a subsequent cancer? It's high, and how high and what type really depends on the radiation, and there probably is a germline component to that. How well is your germline carburetor set to handle high dose or moderately high dose. The low dose is it's really an enigma still, even though we have, we're charging ahead with more analyses in individuals who had exposure following the Chernobyl. We can figure out which ones we think had radiation induced, but then the question is, how do you standardize that and go to the population at large and say these are the people who are really at risk or who are not? And that's still a challenge. And I think the low dose world is one that we all want to know the answers to, but we don't really have really great epidemiologic studies. Even in this country, we have some very large sort of retrospective collections of individuals, but we don't have the sort of scrupulous, really rigorous analysis that Chernobyl has afforded us to say, these are the things that we can put together in an integrated analysis and come up with the following conclusions.
Did we learn some things from Chernobyl that were applied after Fukushima in terms of protection or follow-up of patients or whatever?
Well, there's no question that the experts at the time of at the time of Fukushima turned to the survivors of the atomic blast and the Japanese study, the RARF, and a number of the individuals who were working at the time on both Chernobyl and remember there's nuclear testing on the Pacific Islands in the United States. I didn't really touch upon that. Again, those are generally small numbers of individuals. And so then the question is, can you identify what would look like very small effects with low doses? Remember, as I showed in that one of the first slides, the amount of radiation, that we saw in Fukushima in the environment averaged less than 1/10 of what we saw in Chernobyl. So, there is risk. You can't say that it's not there, but it's much smaller. And so I think the transgenerational study was very helpful for the Japanese, and I still go to ACR and usually have a few requests from the Japanese to talk about it even more.
So it looks like the greatest risk was in children and the iodine exposure. Now, and so one of the questions is, should there be something in place in terms of quickly handing out iodine to block and so on?
That's a great question. That's debated, and depending on what your basic nutritional background, what your nutritional status is, there are places in the world that have potassium iodine ready for that for the population. And who do you go to? You go to your most vulnerable, which is your young children, and potentially to your older, because you do see effects in older individuals, but where we're most worried are the 18 and unders, or 20, depending on where you make that public health cutoff.
So among the audience, there was someone who asked about the nature, the histology of the specific cancers occurring. You mentioned both follicular and papilloma type cancers. Maybe you could just comment a tiny bit about that.
Our analysis that I concentrated on was papillary thyroid, which is the most. If someone has a radiation induced, papillary is by far the most common. It's a highly differentiated, and what was really valued to us was, again, we had the best terrific dosimetry experts, but we also had 6 pathologists from different countries who looked at each and every one of the samples well before we started to make slices and go do genomic analysis. So, the misclass, we wanted to do everything we could to decrease misclassification and draw in things that really aren't that particular entity. And papillary thyroid is very interesting. And what I didn't mention is when we look at the radiation-induced one, the one thing that was left off that slide, I just, in recollection, is we saw basically, the same distribution of sex that we saw from the exposure, as opposed to, if you look at the sporadic background in the United States, or for now in the Ukraine, it's 3 to 4 to 1 young women to young men per se. But following that, we saw closer to 1 to 1 in those cases that we think are radiation driven.
Thank you. There are some other questions for you, but I'll return to you later.
Okay.
I'm just going to turn to Dr. Sabetti and her talk. So one of the things I was wondering is just a remarkable system that you've put in place. But one of the things that I think people may need to better understand is what kind of systems are you using for your your hub and spoke? Are people using their cell phones to send the information from the furthest distances? Are there computers? In other words, how do you get the most remote areas to quickly send the information that you need? And it wasn't clear to me whether you had phone apps or something else. Maybe you could just describe that in a little bit more detail. You're muted.
It's a little bit of all the above. So we have these. So Lookout is our flagship platform, and the way we have Lookout designed, and that's with Ben Fry and the Fathom Information Design team that I've worked with for 2 decades with. We designed it so it can take data from any kind of, it takes on in all SORMOS data, it takes all of DHS data, took all the data from the National Public Health Agency of Sierra Leone. So we're designed to embed any kind of data stream. We work with RedCap, we work with Demagi. So we're really here not to, it's mostly like making things as interoperable as possible so that any data stream can come in. We do also have our own data entry apps where we have given our teams in remote areas computers, iPads, as well as things that they can do on their phones as well. And during Ebola, Andres Colubri, now faculty that was a postdoc at the time in my group, had built apps to collect data for both Ebola and Lassa, so on cell phones. And so that the approach is really one where we have been building our own apps. And during COVID, we had something called Scout that paired with Lookout, where individuals could share their data in real time. So the main thing we really are doing is building an ecosystem that can take in all that data and analyze it, and now embedding more and more AI and into those systems. But we do have our own apps that we've also developed to be paired with those.
So I noticed in some of the pictures that in the remote areas, people were actually using some diagnostic tools. Obviously, they weren't doing their PCR out there, but it looked like there were some tools like we all have here in terms of doing influenza or COVID-19 tests. Where people could take their own nasal swab and somehow put it in the system. It looked like you had systems like that. Is that what you were delivering to those sites?
Yeah, we have ourselves been building CRISPR-based diagnostics for point of care, point of need testing.
Okay.
And so both with lateral flow strips as well as with partnership with DX Labs, where we, during this recent Mpox outbreak, we went out and did testing on the ground, with basically a handheld battery-operated device. We also have partnerships with OraSure and a number of others. So again, we are building a lot of the technologies to design assays, and whatever and we hope that we are doing something that helps all players. So the AI assay design that we're creating, we're sharing that openly and making it available to any diagnostic developer. With the idea that when the next pandemic happens, we want everyone to have real-time assays that are going to work and be robust to viral evolution.
What are your future plans for moving from the, you've already got a number of countries that you're working very closely with. Initially, some were working better than others, but it sounds like you've more uniformly gotten this Sentinel system established in those countries. What is your ultimate goal, both in Africa and beyond?
We are building systems. We talk a lot about why did we start with Africa. Part of it is that obviously they have a high density of the outbreaks of deadly viruses. And so there's a real, interest in there in supporting those communities, but also because there's a real opportunity. The leadership is very informed. I serve on and I still serve on the what we call STAGE, the Sierra Leone's presidential task force. And during COVID, it was one of my favorite meetings. It was a weekly meeting for several hours, and it was, the leadership in a lot of the West African countries we work with are very nimble, very thoughtful, very informed. They all kind of know the mission and work really well together. So we actually think it's not just a place where there's a lot of devastating outbreaks, but also real leadership and understanding and community opportunity to do something. So we think it's a great place to model a system, but the intention is to build these systems and support countries everywhere. So we work closely with the US CDC. Through a grant with them, we also have, we've worked to build that lookout dashboard into the Mass Department of Public Health's data systems. And so it's working behind their firewall to help them. And so that the idea is really to get support to have it, help public health labs across the US as well, and around the world. Whoever wants to work with us, we're building those data systems to be very interoperable and available to all.
So it sounds like with this system in place, you can respond more quickly when outbreaks are small. I'm trying to think how to put this. How big an outbreak does it need to be for you to say, okay, let's activate the system and get going? Because obviously, people get sick all the time, and many things are just individual cases, and it's hard to apply your system to single cases. So what do you use as your trigger?
I think that's a great question, and it's sort of how you want to define it. I mean, I think the idea, what is interesting about infectious diseases is the same thing that allows you to identify singular cases and help impact them is what helps you respond to an outbreak. So the system is created to deal with any level and scale of the outbreak. So you don't want to switch over your system, switch over your response efforts when a pandemic happens. You actually want to build something that you have like a regular good experience with that then can be modified. So, the one thing about, like, for example, that Delphi platform, the Bayesian phylogenetics, what's great about it is, it can run thousands of genomes faster, in minutes on your laptop, compared to weeks and months otherwise, but it also can scale to millions of genomes. We kind of, I think that Patrick Verley, who runs it, sort of says the system has failed when we're at millions of genomes. We don't want to get there, so we're trying to really build intelligent systems that activate and respond earlier. But you're triggering at every point. Like, for example, right, that there was less than 200 cases of yellow fever, but it activated this mystery. It was 179 deaths. That's too many. Even one death is too many. So how do we identify individual cases? And then that idea that if you have it across the system, you can start to identify what is a cluster or what is a moving target. And we spent a lot of time with this idea of spot the anomaly. There are multiple ways of spotting an anomaly. One is just an uptick of cases that you're seeing the actual cases themselves. The other is if you sequence the genome of the virus, even if you only have a handful of genomes of the virus, you can use that handful of genomes to interpret things like reproductive number and doubling time. So, another way of spotting the anomaly is just sequencing those pathogens and understanding what their spread looks like. So those are the types of things that we're using to get the trigger of what level of warning. But I think broadly, we can do much, much better of deciding, like, if we have enough data across enough outbreaks, across enough regions, we can really start being more rigorous and formalized about what triggers a local emergency, a national emergency. So I think we have better data in the system. We'll get more rigorous about that. But essentially, we want a system that's responsive to anything, but that knows when to alert different levels of kind of urgency. But we also have it. The other thing about the lookout is it's created so that the local person has like a deep system that has all the information, including each person in their community's details, if that's what is needed. But then that filters up to the CDC or the Africa CDC, where they get the level that they need, and even to the public, where they can see things at a summary statistic level or at anonymized levels, so that anybody can engage with the data and be able to help the response.
So a sort of tricky question is, you've learned a lot from what you've done in Africa, and obviously, your ultimate goal is to bring this to other countries in need of this kind of system. Do you think there's something about Sentinel that you wish to apply in first world countries, including our own here? Or do you think systems are already sufficiently in place in those countries that you don't need the Sentinel system? I mean, my own bias would be we still need something here.
Certainly. Yeah, no, we have been proselytizing like the idea that America's not ready for a long, long time. And most of the funding agencies that I've been to for decades now, I think, really putting it into high gear in 2014 during the Ebola outbreak. I wrote a bunch of position pieces talking about how the U.S. is very ill prepared. And that if we can't do it here, how do we expect to? Because at that time, the feeling I think people had was like, oh, we're fine, but we need to help other places. And it was pretty clear to everyone, that I was working with that, America is very ill prepared. And I think that came to, full showcase during COVID. But no, I mean, and in a lot of ways, it's even more difficult in the U.S. because we have entrenched systems and IT, siloed IT, bespoke IT in lots of different places. So it's like, not only is it not fully good and integrated, but people are really resistant to changing whatever system they have. And so,
but maybe this could be applied at the state level where, I mean, in some ways we're just too big a country to have one size all over the whole country, but states are pretty good at instituting things. And I'm wondering if maybe some pilot in a few states might be the way to go.
Yeah, I mean, honestly, even just we've been working towards we've been pushing this idea of a city pilots for a long time, and we are kind of getting towards some really good adoption across with the Massachusetts Consortium on Pathogen Readiness, which is headquartered at Harvard Medical School, but really it consists of institutions across Massachusetts, and our Pathogen Genomics Center of Excellence, led by the DPH. We've got a lot of connectivity to say, could we just, in Boston and in the surrounding areas, could we really start piloting what it looks like to have like end-to-end systems for detection? And we proposed for a long time why we think we believe it should be many local hubs. Obviously New York being another big one. Like a lot of different cities should have this. But one of the reasons we think Boston's really good is just because it has 110 institutions of higher learning and college kids coming from around the country and the world constantly. So we've got this we both have these congregate living facilities that are their own incubators for outbreaks. But then with this an ecosystem of a lot of travel and moving cities. So
so sort of a pilot locally.
Yeah.
Okay, very interesting. There were some questions that came in now for Dr. Chanik. One that really is asking you to re-go over some of the germline studies, and the question was, have your analyses found any common variants or rare variants, in germline, with respect to susceptibility to developing secondary neoplasms? It sounds like you didn't find anything, and maybe you just need to emphasize that.
Well, no, we didn't find them for Chernobyl. There are studies. So, for instance, in childhood, the survival study, the large CCSS, 35,000 childhood cancer survivors, in the St. Jude study, there are some variants, the mainly common variants that have been identified through genome-wide association studies that are associated with increased risk for a subsequent cancer. Okay, not necessarily the same cancer coming back, but if someone had, received radiation therapy for bone tumors such as osteosarcoma, getting leukemia 7 years later. So again, some of those things have started to emerge. In terms of rare variants, there are very well-known rare, highly penetrant mutations that, and this is a long-standing argument in the P53 leaf Romani world is, do those people who get radiation have increased risk? And it's hard to sort out whether that's due to the fact that they're at risk for having multiple cancers. Someone with leaf Romani syndrome from the sort of the surveillance MRIs are shown every 5 to 8% per year will have a cancer shown up that was not clinically apparent at that time. I think that part of the problem is the numbers are really are small, and so to be able to say there's a robust finding, you really have to get to very, very large numbers. And the cancer world has focused on characterizing tumors and doing genome-wide association studies in sporadic disease, in looking at familial clusters, but not really come together well enough to address this. There are like a select number of genes that are very important for risk of subsequent cancers. But with respect to radiation, only a handful of those go beyond sort of a Bayesian view. Oh, we see this in the cells and we therefore infer this, and we, are looking at a association and assigning causality to it on the spot.
Well, thank you. There's a question for Dr. Subedi. Despite the new tools in place since 2020 and all the work you've done, are we more or less prepared for a pandemic? That's a general question, and sort of, and again, turning to our own country, with which I asked you about. What are the most vulnerable parts or weakest parts of these links, both here and abroad, with the loss of USAID?
Yeah, so I'll actually point you to this paper. So I didn't get a chance to talk about this particular thing, so I'm going to just share my screen real quick.
Sure.
Here we go. So can you see that? Do you see that we aren't ready for the next pandemic? This can improve. You see it? Yeah. So I'll let me start to answer that question, and then I'll come to this. Basically, with the tools and the technologies that we have, I think that we've made massive advances during COVID. Obviously, Operation Warp Speed being a fundamental, major one, but also in a lot of advances in our technological development, and now we know what it's like to mount diagnostic testing across the country, and everyone is much more aware of an outbreak. We also have greater, on the one sense, we're much more informed as a citizenry and positioned for an outbreak. On the other side, we've developed antibodies to the political maelstrom of an outbreak, and so we run this simulation. It's called Operation Outbreak. These are high school students in full PPE. This is like Time Magazine came to one of our simulations and showed these students participating in an outbreak. This one was set in a gym, and they have basically, here they are in their gear, and they've got their different groups kind of engaging. But you'll see here, like, basically this dashboard that we've created. There's an app that they have that spreads a virtual virus via Bluetooth on their cell phones, and allows them to participate in like a real world scenario where they're trying to stop the outbreak while taking on these different roles. I think those are the main pictures from that one, but you can kind of see more about it on our website, Operation Outbreak. Let me actually then go back to stopping my share. Sorry, this is a little bit, again, stop sharing. Okay, so within the context of that, I would say that we are more prepared from a technological standpoint, but less prepared from a standpoint of societal. So when we run these simulations before COVID, we actually saw everything that you saw during an outbreak. We saw immunity passports, we saw faking of immunity passports, we saw, vaccines being created, we saw government hoarding those vaccines for themselves, we saw political protests. We are able to show that essentially, like, that these simulations will really tell you about societal preparation for an outbreak. When we run the simulation since, we have a lot more awareness, a lot more understanding of what they're dealing with, but we also see instances of full societal breakdown and militia, and full basically anarchy. And it does tell us that if an outbreak was to happen in the United States, that probably militia might come out. People are not going to stand for a lockdown. So it's ever more tenuous. And you can obviously see the discourse right now around vaccine preventable diseases. We're in a worse of a scenario. So we need to start building back that infrastructure now because we're not going to be in a position to handle it when a real outbreak happens.
Harry, can I ask a question follow up to that part of
Yes, please,
terrific
please.
talk. No,
We actually encourage.
the question of what you've set up in Africa is just it's superlative. The question in this country is crowdsourcing, because we saw during COVID that there was a certain degree of crowdsourcing that was very effective, and on both sides, for and against various things. But with your technology and the availability of that, how do could you really use crowdsourcing to your advantage and be able to ferret out the more nefarious use of crowdsourcing for public health good? I mean, that's the hard part about crowdsourcing.
Yeah, I mean, that's the thing. You're always doing that kind of the road to hell, the path to hell is paved with good intentions. Even when we built this Operation Outbreak game, where we're trying to teach kids about how outbreaks spread and try to help them understand how viruses spread between individuals, to understand their own collective knowledge base and how they can work. We see characters within those games that are spreading misinformation, that are causing trouble, and is teaching them more about how outbreaks spread, good or bad. It's very tricky. I mean, I think at the end of the day, I often sort of say the line that outbreaks expose and exploit the cracks in our society. So any trouble we have now is going to be 10 times trouble during an outbreak.
Yep.
And I think the only way towards it is just to keep building systems and working together. I don't think that the version that we had, which is sort of to treat the citizens like in an antagonistic way, worked. So I think our only hope is to work together, and we have to do things like one of the things is we also had Bluetooth-based apps that do contact tracing. We started building those back in 2015, 16, and when we did that, though, a lot of our work was around privacy. Like, there's no reason why we need to know your name or anything like that. We just need to know how to contact you. We don't need your information after you've stopped having the infection. We could give you burner phones. We can do things to make it easier for you to engage with us. So really maintaining the trust of people is really important. But again, that is not looking good if you look around with the news around the world right now. But that's the that's the work that needs to be done.
Right.
Well, this was just super. I think what you've both shown is that there's at least three components here. There's high tech, and there's building structures to analyze events. But you both emphasized so much that this is a social issue as well. That to gather information about radiation exposure, to gather information about potential outbreaks requires a community, basically a village, to work together to make all this work. So I really appreciate what you've both presented today, and I assume our large audience from today's meeting really learned much from both of you. So thank you so much.
Thank you. Yeah.
Thank you very
Thank
much.
you very much.
That was magnificent. We appreciate your being with us. There are a couple of minutes, maybe, if you would comment about your thoughts in the future as to the role of population study. Well, I guess we're off. Okay.
No, we're still on.
Oh,
still on.
I was going to ask about your thoughts about learning machines, computational biology. Are there ways in which instrumentations of that type can provide clues which we are not so, we are not aware of, even with the technologies that we currently use? Could you perhaps both in our closing moments comment about that future world?
I would say the future world, it's exciting to think about that, but the capacity of our computational abilities is dependent upon good data going in. And picking up on something that Partis said, that a lot of the misinformation and the mistrust doesn't get weeded out. You don't have somebody cleaning the data so that you say, all right, what we need is the scientifically rigorous data. And we live with this in cancer all the time. People have clusters or claim that things down the street or 5G are causing cancer, but we don't really have that evidence. It's a challenging thing to do. I mean, you can find information, but P.T. Box, the famous statistician, said all models are wrong, just some are informative, and you have to know when and where it's informative. I'm not as optimistic that AI is going to solve these things. I worry that more things will come from it that are problematic. I know, Pardis, you're smiling.
Well, I mean, that's a lot of question in a question, and especially in a couple of minutes to go to the end. I mean, from just more practically, like I showed you in the talk, our talk, this technology called Lyra. We put a preprint out, and we're now in kind of late stage revisions on that paper. But we were really trying to the kind of one of the goals of this was this idea of democratizing data analysis, and what we were trying to do was to make an AI form that could be run by anybody on their laptop and could take in less data. What we found in the end is what was really exciting is that we use state-space models, which have not really been used that much in biology. As many people focus on LLMs, and we showed that it's something that's subquadratic and can work really, really efficiently, but it also modeled epistasis well, and in many cases set the state of the art. So we were thrilled by that. And as we kind of talk about what we're excited about that, it's that imagine in biology, one of the reasons why AI has not transformed biology the way that it has some other fields is the sort of limitation of data and the expense of gathering data. And so in order to test a hypothesis, you have to go out and you have to generate vast amounts of data for millions and millions of dollars. You have to hire ML people in an environment where really good ML people are going to go work on problems that make more instant money, and need a lot of money. And then you need to train those and set up foundation models and spend months training those models. And so pretty much a lot of our scientific questions in biology are dead on arrival just because it's just too hard to get anyone there. And what's exciting about Lyra and other things using state spaces is that you can do it with much less data. You don't need to pre-train. It really understands biology. And so with very limited data, you can start to ask those questions. Anyway, so that's like a long practical question of, I think there's going to be some breakthroughs in biology that are going to allow us to do some really powerful things with much more limited data sets, and really drive. So I'm very excited about the future of AI in biology. Kind of, Stephen, to your question, I'm, yes, of course, always very concerned about AI and humans, and what we do with them and where it all goes. And certainly there are a million which ways to Sunday that it all can go sideways. We recently wrote a paper for The Hill that said, essentially talked about some classic examples of making bioweapons, and then talked about adding AI into that capability. And and it's going to be terrifying. And so we have a lot of work to do to get to the point where AI is not misused, and societies work together, and we are very far from it. But we can get there. We can get there with good people, and meetings like this make me feel good. It's always really a pleasure to be with folks from the NIH, particularly I'm just very grateful to be here and talking with you all.
Thank you so much. Thank you.
Bravo.
Thank you. Thank you very much. It's been a pleasure.
Okay. Bye, everyone.